So now we will start chapter 5. Chapter 5 are about the planarity and minor. So in the undergraduate graph theory, we learned about the concept of planarity and minors. There we define several notions. So let's quickly go through it. But you might want to take a look at the chapter 0 of the lecture note and quickly go through the notions or concepts defined there. So we define the drawing as a map which maps the graph onto some surface. And it maps the vertices into points and edges into continuous curves. Moreover, when we have the vertices embedded, and then when we embed say you have U and V, when we embed the edges between U and V, it embeds into a continuous curve whose end points are the U and V. So which is what it means by preserving the incidence relation. And we define crossing as a common internal point of two edges. So let's just call the image of this map as edges and image of this map as, again, vertices. So if we say edge, it could mean the edge of a graph or edge of or this continuous curve when it's embedded. So for given this drawing, we define this crossing as a common internal point of two edges. And we say this drawing is actually an embedding if it doesn't contain any crossings. And we say that a multigraph that can embed into a plane is planar graph. And specific embedding, we call it a plane graph. And once embedding is given, say this is one embedding of a cycle of length 4. Then in the surface, if you delete the image of this embedding, then you have two connected component. So inside, this is one open set which remains, or outside. And those maximal connected components are called faces. And we learned about Jordan curve theorem, which says that any simple closed curve divides the surfaces into divides the plane into two faces, inner face and outer face. And we also define these things in more rigorous way in the undergraduate graph theory. And we learned about several concepts like Euler's formula. So when we have a planar graph embedded and we count the number of faces and we count the number of edges and vertices, then they are related. And also we define this minor, which is a more general concept than subgraph. We say that H is a minor of G, or we say that G contains an H minor if we can obtain H from G by deleting edges or deleting vertices and contracting the edges. Here, what I mean by contracting an edge is that when we have this graph, then you have this edge E. Then what we do is we take the end vertices of this edge and we slowly merging them together while making this edge short. So you get this. So for dealing with multigraph, you can consider, say, if there is this edge, then these two edges might become, two multi-edges here. But when we consider simple graph, then we delete the multi-edges or loop. Some cases you say that this is still here as a loop. But depending on several contexts, we either leave the loop or leave the multi-edges, or when we deal with simple graph, we can just, delete them and then remaining thing as the, result of the contraction. So that's the definition of minor. And then we learn that a graph is planar if and only if it doesn't contain K5 or K33 as minors. So these two are the essential, obstruction for a graph being minor. And Kratowski's theorem says that a graph is planar if and only if it does not contain K5 subdivision or K33 subdivision. So those are equivalent. And also we learned some theorems about the coloring planar graph, which is related to, which was motivated by the map coloring problem. So it was conjectured that when we have a map and we want to color the countries with different colors so that no two adjacent countries get the same color, then it's conjectured that as long as we have 4 colors, then we can always complete this no matter what the given map is. And as planar graph has no K5 minor, and it is known that it can be colored with 4 colors, you might be wondering the relation between this 5 and 4. And then that was conjectured that by Hedwiger, that the graph without any case of t plus 1 minor is t colorable. So this is still open. So that's some concepts that we learned in the undergraduate graph theory. We have quickly gone through. So first thing we want to deal with is how one can test the planarity. So for a graph is given, when graph is given, can we check whether the graph is planar or not in an efficient way? Or can we actually find the planar embedding? So what we want to learn is we want to learn some way of, actually checking the planarity of graph and producing an actual planar embedding. So for that, let's define some concept. Assume we have 2 graphs, graph G and a subgraph H. And we define an H fragment as follow. So it's either an H which is not in H, whose endpoints are in H, or a component of G minus vertices of H, together with the edges which connects G and the component and the vertices in those edges. So for example, if we have this G, this entire thing is G, and this black graph is H, then if you consider this edge, so this edge let's add this and the vertices in the edge. So this edge is an edge not in H. Oh yeah, this might be. This is an edge not in H, but whose endpoints are in H. So this satisfies the first condition. So this is an H fragment. And also, if you consider, this H, in G, if you delete this, then what's the component? You have this component and this component. So you take one component and you consider the edges which connects this component to H. And we also include these vertices. Then this is H fragment. And we call these vertices in these edges connecting this as the vertices of attachment to H. Again, you take this component and you consider the edges connecting them. And this is another H fragment. And these are the vertices of attachment. And let's just call that these two vertices in this edge as, again, the vertices of attachment to H. So, why do we consider this? If we have a H, this H is embedded in, if you just consider this black part, this H is plane graph. It's embedded on the plane, and there is no crossing. And if we want to embed the rest of the vertices, then what do we have to do? This part must be embedded in here. So meaning that if we want to, there is this, crossing. In order to eliminate that crossing, and we want to embed this in a planar way, then only possible way is you embed this inside of this face. So the only possible way is that we choose this face and we embed this H fragment inside of this. By the same logic, this component, this H fragment, where was this? This can be only embedded in inside of this face. So you have to embed inside of this face. So later in the algorithm, what we want to do is when we are given G, we want to embed, graph bits by bits. And H is the part which is already embedded on the plane. And then remaining thing is not yet embedded. We haven't decided how to embed them. And then now we want to consider each fragment, and then we want to decide which face is this fragment goes. But sometimes there are more than one option. So for example, this fragment can be actually instead embedded here. So either this or this, there are more than one way. But that motivates this. That's the motivation of defining this H fragment. And moreover, when we actually embed this fragment is actually a fragment of this cycle as well. And this fragment is also this cycle, fragment of this cycle. So this H fragment, as long as the entire graph is planar, if this H fragment is actually not this cycle fragment, and then there is this H, then there is no way that we can embed this no way that we can embed this fragment into the plane without changing how we already have embedded the black graph. So as long as we are not stuck. So in order to avoid the situation that we cannot embed anymore without modifying the previous choices, these fragments are always the fragments of certain cycle. And moreover, if we have a cycle and then there is some fragment, say this fragment, and another fragment, they are like, if they are like, looking like this, then in a planar embedding, they cannot be both inside of this face. We have to put one thing outside. And if you go back to the proof of Graph-Topolsky theorem, what it essentially does is that if there is no K33 minor or K5 minor, then we can always put this kind of fragment either inside or outside, so that they are not so that they are not conflict each other. All the things inside doesn't conflict each other, and all the things outside doesn't conflict each other, in the way that if we define this and this conflict, if they look like this. Anyway, because of those motivate us to define these fragments of a cycle. So C is a cycle, and we say that two C fragments conflict if this kind of situation happens. So if they have three common vertices of the attachment to C, then we say they conflict, meaning that we have a cycle. And if we have this, and say we have this, then they conflict, because in that case we cannot draw both of them inside the face or both of them outside the face, so they are conflict. And or, as before, if there are four vertices, P1, P2, P3, P4, so that in cyclic order on C, such that P1 and P3 are vertices of attachment of one C fragment A, and P2 and P3 are vertices of another attachment, which is C is a piece of vertices of attachment. And let's define an auxiliary graph, which is called conflict graph of this C. Is a graph whose vertices are the C fragment of G. So this is one fragment and this is another fragment. Let's say this is one vertex 1 and this is vertex 2. You just give name. And then we add the edges between two C fragments in here if they are conflicting. And conflicting fragments are adjacent. So for example, if we have this, then in the conflict graph we have black, red, blue, green, which represents the each fragment of the color, and these two conflict, and these two conflict, these two conflict, these two conflict. And let's say one more purple is here. No, let's just, okay, let's not do this. Anyway, so this defines this C fragment, conflict graph of the C. So this conflict graph, essentially if we have a planar graph and then we have certain C and we consider the conflict graph, then all the fragments inside the face has no edges between. They don't conflict each other. All the fragments outside, they don't conflict each other. So that means this conflict graph is bipartite. We put every vertex which comes from the fragments which are inside C here, and then all the fragments which comes from the fragments which are outside here, then that's a bipartition. Actually, in 1958, Top proved that the G is planar if and only if complete graph of each cycle is bipartite. And Kelman and Thomassen proved that every three connected non-planar graph with at least 6 vertices contains a cycle with 3 pairwise crossing chords. So remember, chords is when you have a cycle and then there is edge connecting 2 vertices. That's chord. So using this so this shows that when we have non-planar graph, then we have a specific substructure. And by using that, there are various fast algorithms for testing planarity of graph. There are linear time algorithm there are several, like Hopcroft and Tarzan in 74, or Booth, Recker, 76. Linear time algorithm to check planarity. And which are quite complicated. And Boyer and Wilbur 99 or Hu 2001 prove a simpler linear time algorithm. And what we'll learn is more simpler version of quadratic algorithm. Let's use the fragments. So this is what we will learn. The basic idea is as before. We have already embedded some parts, say H. And then now we see the fragments. And then each fragment has to be embedded into a specific face of this given embedding of H. This H gives face, this face, this 5 faces, 6 faces. And for this fragment, this is the only face that can be embedded. And this fragment, this is the only face that can be embedded. For this fragment, there are 2 choices of embedding. And we want to make choices and then embed each fragment one by one. Keep extending this H. So that's a basic idea of how we will prove this. So in the next video, we describe the algorithm, their algorithm of embedding graphs onto plane. And this algorithm not only checks the planarity of the given graph, but also produces one particular planar embedding.